45. Yep. It'll be 20 to 25 minutes. There's not a whole lot of information on each slide.
Okay. So is everyone here, Derek?
I think so. Yeah. They're not here. They were not invited.
And are you recording?
Not yet. I should do
that. How do you feel if people have questions in the middle of the presentation? You want them to raise their hand or type in chat?
When they raise their hand, does it show up on my screen? Do I see that?
So what you could do is you can click on participants, and then it should show on the side. And then if they raise their hand,
participants is not showing up on the side. Should we just save questions for the end then?
Yeah, we can save questions to the end. That'd probably be easiest.
Let's just do that.
Okay, well, let me go ahead and introduce you. So today we're going to have the defense honors college thesis defense for Derek Dardzinski. Derek was very tenacious. He sent me probably 60 or so emails to see if I have a place for research in my group, and I think I finally replied after the 60th and said, well, let's talk. And actually it was one of the, I've really enjoyed talking to Derek. He's interested in the science. He's interested in the engineering of everything he's been working on. He did take the dark turn of going towards theory as opposed to experiments, but it's pretty exciting. He's going to be going off to Carnegie Mellon for grad school in material science. He got the award for undergraduate leaders in chemical engineering, got to go out to North Carolina State and give a presentation. He's been very successful in all the different things that he's worked on. We've thrown a lot at Derek, and he seemed to enjoy just about everything that we threw at him. I really enjoyed watching you excel with the XPD code and get those calculations done and plotting them up. So today, essentially what Derek's going to be presenting is the research from his honors thesis, which is looking at the reactions of molybdisulfide with water using ambient pressure XPS. So Derek, feel free to go.
Alrighty. Okay, so we will take a look at the investigation of MoS2 with ambient pressure X-ray photoelectron spectroscopy. And as Dr. Herman said, this is my honors thesis defense. Okay, so I'll start by going over what we're going to talk about in this presentation. So I'll start with a little background about what the issue we're trying to solve is, a little bit about 2D materials and XPS, and then we'll go over the materials and methods that we used, go over some results, and then finally discuss all the results. So starting off with our background about why we're actually doing this project. Essentially, we are in need of cheap catalyst materials for hydrogen production with the hydrogen evolution reaction, and that's for clean energy applications. And then the hydrogen evolution reaction equation is right here. So you have 2 water molecules combined with 2 electrons, and then that forms 2 hydroxide ions and hydrogen, which is the desired product. Currently, platinum is the best material for this reaction. However, it is expensive and it's rare, so that limits its application for industrial scale hydrogen production with HER. So our solution to this problem is to use molybdenum disulfide, which is a cheap alternative to platinum for catalysis. However, we know that the basal plane, the top surface of MoS2, is known to be chemically inert. So in order to activate the surface, we can induce defects, and then these defects can either be anion vacancies or heteroatom dopants. And you can see on the right-hand side, you have band structures for a pristine MoS2 surface, an MoS2 surface with a sulfur vacancy, and an MoS2 surface with a platinum atom on top. And in the sulfur vacancy and platinum atom band structures, you can see that some gap states are forming within the band gap of the bulk material. And those essentially reduce the free energy of hydrogen absorption. And so that helps the HER reaction go. And also the defect sites increase the local conductivity of the material. And then that increases the charge transfer, which helps donate electrons. And so overall, we're trying to increase the chemical activity of the basal plane of MoS2 by inducing anion vacancies, heteroatom dopants, so platinum on the surface. That'll be a different experiment. And now we'll discuss 2D materials a little bit. We'll start off with MoS2, which is our material that we're going to work with. The structure of MoS2, it's monolayers held together via weak van der Waals interactions. And so you can see on this structure, you have the layers of molybdenum atoms sandwiched between sulfur atoms. So molybdenum is the greenish blue color and sulfur is the yellow. And then we know that it has chemically active edge sites and an inert basal plane. And some interesting properties of 2D materials is that from the layer structure, it gives rise to some unique electrical properties. So you can see in these band structures that the band gap of MoS2 increases as the layers decrease. So we have bulk MoS2, which has a 0.76 EV band gap in this band calculation. And then the monolayer MoS2 has a 1.84 electron volt band gap. And that is due to some quantum confinement effects. And then MoS2 also transitions from an indirect band gap semiconductor to a direct band gap semiconductor. You can see it's indirect here and then direct here. And so for some of these interesting properties, most HER studies with MoS2 do use 2D nanocrystals, and that's because there's more edge sites as well. But for our study, we're just using a bulk material. And then some other common 2D materials would be graphene, which has a honeycomb structure, and then hexagonal boron nitride also has a honeycomb structure. And then our material, MoS2, which is a transition metal dichalcogeniide that has a hexagonal structure. And then there's also metal oxides, such as cobalt dioxide, which has an orthorhombic structure. And all of these materials are layered materials in the bulk. Now we'll introduce the main characterization method, which is XPS, X-ray photoelectron spectroscopy. So we'll start with the applications of XPS, why we actually use it. So XPS is a surface-sensitive characterization technique. It has an information depth of about 5 nanometers, and we'll talk about that why later in the talk, and that covers the first few layers of the surface. And then it allows us to probe the oxidation states present on the surface, and from that, we can then infer the chemical composition. And so the main principle of XPS is the photoelectric effect, and that is when photons excite electrons within the atomic orbitals of the material. And if those photon energies exceed a certain barrier, the electrons will be ejected from the surface. So you can see the red photons coming in here in this cartoon depiction, and they eject photoelectrons. And then the energy of the photoelectrons is proportional to the energy of the incoming light. And then that energy barrier I discussed is called the work function. And the work function is the energy difference between the vacuum and Fermi energies. And so in this image, you can see on the left-hand side, it's a metal, and that's where the electrons occupy states up to the Fermi energy. And then on the right side, you can see a semiconductor where the electrons occupy states up to some valence band maximum, and the Fermi energy lies within the band gap. And as you can see here, the work function is a material-dependent property, so it depends if it's a metal semiconductor, and then what the structure is, what the surface is like, and anything like that. Another important thing that we have to define is the binding energy. So the binding energy is a function of the energy of the source photons, the kinetic energy of the photoelectrons, and the work function of the spectrometer. And the reason we define binding energy is because it allows us to have the peaks from the spectra show up in the same position, no matter what the source is and what your spectrometer is. So it allows for consistent data points. So some of the general components of an XPS spectra would be on the x-axis, you have the binding energy, and that's typically in electron volts. And then on the y-axis, you have counts per second of the photoelectrons. And then also you have the area under each peak, which is the intensity. And this is the important component, which we use for analysis. And so you can see the molybdenum oxide has an intensity here, showed by this pink area. And then the oxysulfide has this blue area, and adsorbed water has this gray area. And so these intensities vary by core level. And so you can see we have the oxygen 1s core level here. We'll also be discussing the molybdenum 3D and the sulfur 2p core levels. And then to compare them, it requires some sort of normalization factor, and that would be the sensitivity factor. So for my calculations, I use the semi-infinite slab model found in Fadley, and that's a function of the effective solid angle, the effective specimen area, the detection efficiency, the density of your material, the differential cross-section, and the effective attenuation length. And you can use this sensitivity factor to then calculate things like the atomic percentages. And so to do that, you take the intensity of the peak and divide it by its sensitivity factor, and then divide all that by the sum of the other peaks divided by their respective intensity or sensitivity factors. And again, it's a function of the same variables as the sensitivity factor plus the photoelectron peak intensity. And in my calculations, I assumed that the effective solid angle, the effective specimen area, and the detection efficiency were all constant, so they could cancel out. And that left the atomic percentage only a function of the intensity, the effective attenuation length, and the differential cross-section. And then to calculate stoichiometric ratios, it's a similar method, but instead you just take the ratio of two peaks divided by their sensitivity factors, and that is a function of the same variables. And again, it's just reliant in my analysis on the effective attenuation length and the differential cross-section. And to calculate the differential cross-section, we use this equation again from Fadley, where it's a function of the cross-section, the asymmetry parameter, and the analyzer angle. The cross-section and asymmetry parameter are material and core level dependent, and then also the analyzer angle is system dependent. And then the effective attenuation length, which gives XPS its surface sensitivity, we use this equation, where it's a function of the lattice parameter, the kinetic energy of the photoelectron, and then the average atomic number of your material. And so the reason why it gives XPS its surface sensitivity is because it typically lies on the order of about a few nanometers. And that's the distance an electron could travel within the material before it loses its energy. And if you need additional resources for calculating it, I did make a website which allows you to calculate the differential photoionization cross-section and the effective attenuation lengths if you put in the appropriate variables. And then it's at this link if you want to use it. And now I will discuss some of the materials and methods that we use. We'll start off with the actual material we're investigating, which is our MoS2 sample. This is just a geological MoS2 sample. It's not synthetic or anything fancy like that. And it was purchased from HQ Graphene. Our sample was approximately 2 centimeters by 1 centimeter, but we would break it up into smaller pieces to put into our system. And then the system I'm talking about is our Ambient-Pressure XPS system, just made by Specs. And this is in Johnson Hall, and it has a nice little feature, which is the nap cell, which allows us to do XPS under a pressurized environment compared to the normal ultra high vacuum environment. So this is where we pump in 1 millibar of water vapor into this cell after it's attached, and then our sample will be in here, and we can do XPS within the cell. And then we also use an atomic force microscope in this experiment, and that lets us look at the surface topology and roughness, just to compare what the surfaces of our samples look like when it's clean versus defective. And then for our surface preparation, we started it off with mechanical exfoliation, and we used 3M Scotch tape, which we essentially just stuck to the surface. And due to those weak van der Waals forces between the layers of the material, when you peel the tape off, it also removes the top layer of the material. And so that gives us a clean surface before we start each experiment. So we would exfoliate outside of the system and then immediately put it into the ultra high vacuum load lock chamber. And then after it's in the system, we used argon ion sputtering, which we would accelerate argon ions towards the surface. And then this would remove some of the surface atoms. And so it can either remove surface contamination, or in our case, we really wanted to remove some of the top layer of sulfur atoms to induce defects. And you can see a little depiction on the right-hand side of what it's actually doing. And in our experiments, we used 1 kilovolt argon ions with a 10 milliamp emission current, and we rastered it over a 10 millimeter by 10 millimeter area. And then finally, we annealed our samples, and this is used to degas the sample, so it removes any carbon contamination and oxygen contamination on the surface. And our samples were annealed to 600 Kelvin for about 1 to 2 hours or longer, depending on how much contamination was on our surface. And then for visual people, I made a little schematic of what our experiment looked like. And so we start with an unreactive pristine surface. We sputter it with argon ions to then create a defective surface, which is reactive. And then we would put 1 millibar of water vapor into the system and do XPS and watch it oxidize. Okay, now we'll start to discuss some of the results from our experiments. So the first, material we'll discuss is the pristine surface. So there's no additional defects added onto this. It's just exfoliated and then put directly into our system and then annealed as well. And so after water exposure, we did XPS spectra. Well, there's 1 millibar of water vapor within the system at 300 Kelvin, 400 Kelvin, 500, and 600 Kelvin. And so as you can see in the molybdenum 3D and sulfur 2B core levels, there's N and P type MoS2 showing up on the surface. And that's characterized by a 0.7 EV split between those two peaks, the N and P type peaks. And then you can also see in the oxygen 1 spectra that there's a native oxide on the surface, which would be this pink molybdenum trioxide peak. But you can see that it doesn't grow during the experiment. And so, yeah, it was just there from the start, but there was no growth seen. And then this purple peak is the gas phase water. And if you calculate the atomic percentages of the above spectra, you can see that the MoS2 and molybdenum trioxide percentages remain relatively constant, which kind of seconds the fact that the pristine surface of MoS2 is not reactive, and it shows that it's not oxidizing. So to combat that, we then induce defects on the surface. So we'll now discuss the 1.6 to 1 stoichiometric ratio surface. So we started off with sputtering, and you can see in this sputtering spectra, you see a lower binding energy shoulder develop as the stoichiometric ratio decreases. So it goes from 1.84 after the first sputtering all the way down to 1.6 for our final defect density. So this lower binding energy shoulder is from elemental molybdenum forming, which is at 228 electron volts, and substoichiometric MoS2, which is at 228.5 electron volts, which is right around here. And the final stoichiometry of the sample is 1.6 to 1 after 15 minutes of sputtering. So after we sputtered, then we can calculate the percentages and stoichiometric ratios. So you can see the MoSX percentage increased while the stoichiometry decreased to 1.6 to 1. So this blue line is the substoichiometric MoS2, the MoSX. And you can see also its stoichiometry is getting reduced to 1.6 to 1. The MoS2 stoichiometry, however, remained the same, and that's because its signal is coming from the bulk of the material, because that's not affected through the argon ion sputtering. That's just affecting the top surface. So that's what we would expect. And then also you can see molybdenum trioxide, which is this pink line, its stoichiometry is decreasing, and it decreased down to 1.9 to 1. And that suggests that the oxide is found on the surface and not in the bulk of the material, because it is affected by the argon sputtering. And then you can also see the elemental molybdenum increasing slightly right here in this green line. And so after sputtering, we now can expose it to the 1 millibar of water vapor at the temperatures ranging from 300 to 600 Kelvin. So initially you'll see the oxysulfide and the molybdenum trioxide forming on the surface. So the trioxide is this pink peak, and the oxysulfide is this blue one. And you can also see oxysulfide here in the molybdenum 3D core level, and then you can faintly see the trioxide at a higher binding energy. And so the oxysulfide is at 229.5 electron volts, and the trioxide is at 232 electron volts in the molybdenum 3D core level spectra. And then you can also see this suggests as MoS as oxysulfide, And you see the molybdenum trioxide elemental molybdenum is decreasing. The elemental molybdenum surface. More surface, you can see it fluttering. The low energy shoulder is more pronounced in the 1.6 to 1 sample. And that's because there is substoichiometric MoS2 and elemental molybdenum on the surface. And then this reached a final stoichiometry of 1.2 to 1 after 18 minutes of sputtering. And when we analyze this data, you can see the MoSX percentage increased again, while its stoichiometry decreased at about 1.2 to 1. And then the MoS2 stoichiometry remained constant for the same reason, because it's in the bulk. And then molybdenum trioxide percentage decreased to a stoichiometry of 1.7 to 1, which again suggests that it's just a contamination on the surface. And then the elemental molybdenum also increased slightly, as it did before. And with the water exposure spectra, it's in our Kelvin again. You can again see the oxysulfide and the trioxide forming on the surface, with the pink peak being the trioxide and the blue being oxysulfide. And again, it's at the same positions in the molybdenum 3D core level spectra. And then you can see an even more pronounced decrease in the lower binding energy shoulder as it's being oxidized, which is coming from the oxidation of the elemental molybdenum and substoichiometric MoSX species. So again, you can see that the oxysulfide percentage is increasing while the substoichiometric ratio is increasing. And that again suggests that oxygen is adding to the image of the molybdenum brings of the surface. So updated to that molybdenum 3D course to get the various images of the DNA to the purple one is if you compare the splitter for the substoichiometric mode, you see that the MoS percentage is decreased for all samples, which is a ratio from oxysulfide. And then we can also look at the AFM images showing the surface roughness. On the left-hand side, you can see the pristine sample, which has a roughness of